Exercise 101. So let's do something very basic. This should be done before those exercises. From 80 to 100 we have done before, so those are more basic things on those period rings. So recall. Let A be commutative ring. With unity. And let P prime number. And the characteristic of this ring to be P. Then in this case we call absolute Frobenius. Absolute Frobenius. Map on A. This characteristic P ring. So because this is the characteristic P, this is more over ring homomorphism. This is ring homomorphism because in general it's only multiplicative, but here this is also true thanks to this is characteristic P. So, second part of the definition, if this Frobenius is isomorphism, then we call a perfect ring. It's called reduced if it has non-trivial nilpotence. Exercise, the first small exercise. A is reduced if and only if Frobenius is injective. So non-trivial nilpotent means I'm asking if A has no non-trivial nilpotent. So we want to show then Frobenius is injective. So suppose Frobenius x equals Frobenius y, then this implies x to the power p equals y to the power p. And so this implies x minus y to the power p equals 0. And there is no non-trivial nilpotent. And so x equals y. Okay, conversely it's very similar. So if you start with injective Frobenius, this is telling you that x to the p equals y to the p implies x equals y. Right, and this tells that x minus y to the p equals x minus y equals 0 for any x, y in A. This is telling you that a to the power b implies a equals 0 for any a in A. And now we claim that A is then reduced. Non-trivial nilpotence. I mean, suppose not. If not, then there exists some A non-zero such that a to the power n equals 0. There exists some n positive integer, right? And then this implies a to the power a to the power n to the power p equals 0. And this implies a to the power p times n equals 0. This implies a to the power n to the power p equals 0. Oh, wait. Let's just stop here and a not 0. Not sure. Should I discuss? It's p and n co-prime. Let me think. I mean, can I think of a counterexample to just illustrate this phenomena? How about f3, and then I'm going to add x quotient x squared. So you see there is x bar non-zero, but x bar squared equals 0. So A is not reduced. But then the question is Frobenius injective? Frobenius is for any A mapped to A to the power cube. Alright, so if you have, let's say, I x to the power I bigger equal than integer, this is mapped to cube x bar cube I, but notice that this is mapped to x cube, which is wait. It's mapped to 0. Right. Yeah. So this is not injective. Already this explains it. So yeah, just this very quick counterexample. I mean, this is something very stupid. The problem, it's just, don't even to argue those. So if a to the power n equals 0 for some non-zero, with n the smallest integer, the smallest such integers. Yeah. And in other words, the order of A then let's say up to multiply by some s with s so bigger equal than 0, less than p. This will such that na plus s is divisible by p, right? Because all of those integers divisible by p fall into kind of 0b to p and p into those some kind of lattices, and if your NA fall into some lattice, then there exists some s such that just and s will fall into those points divisible by p, and this is 0. Let's say this equals a to the power m times p. If m equals 1, then this is done. If m is bigger than 1, then what do we say? We say that a to the power m to the power p is 0. So what I'm going to do is I'm going to modify a little this argument, right? I'm going to say that I claim a to the power m must be 0, but now it seems not. Why I can't claim this? I'm going to modify a little this definition of nilpotent. I'm claiming that I can find an integer which is the smallest one that there exists some element to this power equals 0. Let me write it down more clearly. So let me remove this and restate it. What I'm going to do is that I want to show you as no non-trivial nilpotents. If not, suppose so n is the smallest integer such that there exists element of a with a to the power equals 0, right? Because those integers such that there exists some elements to this power equals 0, this is a subset of natural numbers, so there always exists the smallest one. Up to maybe you use X from choice, maybe not necessary, but anyway, let's suppose n is the smallest one, right? And now let's look at if this n is smaller than p, then we have a to the power p. I mean, of course, there is non-zero element. A to the power p equals 0 with a non-zero, and this implies Frobenius is not injective contradiction. If n is bigger than p, then we have this there exists some s, as what I said, bigger than 0, smaller than bigger than 0, smaller than p, such that again integer such that n plus s equals some n prime times p. And now again a to the power n plus s is 0, and this is also a to the power n prime, and then p equals 0. Obviously this n prime is smaller than n. By our assumption, s is bigger than 0, less than p, and so this n prime is basically this is n plus s divided by p, while with this s bigger than 0, less than p, and so s over p is smaller than 1, and this is an integer, and so this implies that n over p plus this integer is less than n. This forces or also a to the power p to the power m prime. And this is also a to the power m prime to the power p equals 0. This force is a to the power p equals 0, because if not, then it's contradicted with n is the smallest integer. So we find some non-zero whose power n prime equals 0, but n prime is smaller than this, contradicting n is the smallest such integer, blah 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 blah. And so this force is a to the power p equals 0. And so again, by our assumption, a is non-zero. This is again satisfies not injective contradiction. And so we are done. So this is just one example to illustrate this phenomenon. So we have proved this first part of the exercise. So let's continue with this second part of the recall. Second part of the recall. We recall this construction. Sometimes it's called functor R, sometimes it's called inverse limit with respect to Frobenius, kind of a perfection functor. And of course, this is related with what is called tilting functor. So let me recall. Let A be a commutative ring. With unity. Suppose the characteristic is again p prime, and we are going to define R of A to be inverse limit. Let me just denote as follows. So Frobenius, or x map to x to the power p. Let me write like this. What does this mean? I'm going to describe. So consists of those elements x0, x1, in direct product of A, just as a set, in product of A as a set, Cartesian product of A as a set, such that x n plus 1 to the power p equals xn for any n integer natural numbers. Okay, so as a set, this is a subset of A. So its elements satisfy this relation. Exercise 2. So under the above construction, this is a perfect ring. Perfect row characteristic P, if I want to be more precise. So let's prove this. So I've defined let me think, should I mention this characteristic at this moment, or should I define it later? Because I haven't really given it structure at this moment. This is, let me think, as the inverse limit of a ring. Yeah, I already give it a ring structure. So let me just prove more basic things here. I'm just going to prove that Frobenius defined as, for any type of elements, map it to component wisely to the power p is isomorphism. That's what we really want you to prove here. Okay, so let's prove this. Yeah, later, sure, this will be a characteristic P and complete valuation ring, and we can describe the residue field. Many things to discuss, but at this starting point, let's just prove this more basic thing. So this is very easy. So suppose you have element which is mapped to 0. What I'm going to, sorry, wait for a while. So let me show this is a ring homomorphism, and then yeah, I really, if you really want to state this more clearly, you have to tell what is the ring structure of RA, right, reasonably. So let me just prove more elementary thing. I'm just going to prove that the Frobenius defined, so on RA, the Frobenius defined is a bijection. Let me prove. As I said, this will be a ring homomorphism after I precise what is the ring structure of RA, right? As you could say this, you cannot really just say this is component wisely addition and multiplication, because otherwise this condition might not be satisfied anymore, right? Because because if you have, let me put a remark, if you have x0, x1, and I have y0, y1, if I simply define this to be component wisely, then it's okay if characteristic is p. And so this is okay for addition. For multiplication, I need to do the same. Yeah, let me see, just component wisely, let's define the multiplication. And then, all right, this is still okay. This is commutative. This is okay, so you could define your ring structure here. Anyway, let's first prove this is bijection. So if Frobenius acting on x0, x1 equals Frobenius acting on y0, y1, and then this tells that x0 to the power p, x1 to the power p equals y0 to the power p, y1 to the power p, and then implies component wisely. We have this, and because this is characteristic p, it's telling that this is 0, and again, because this ring is assumed to be if you assume this A is reduced, then this tells you this is that way, right? But we don't assume this is reduced. And then what can we say? This is telling that xi to the power b, this is xi minus by the fact that this element is taken from Ra. This works for any I. For any I actually bigger or equal than 1. And so this is telling you that x equals y at the beginning. Call this x, call this y. And so it is injective. Right. In particular, this is telling you that R of A is reduced, even without, right, by exercise 1, this is telling R is reduced, even if A is not. Conversely, let's show the surjectivity. So for any x, let's say for any x, yeah, in Ra, we claim that this x1, x2, kind of, we are just shifting to the left by 1 position. What we are doing is actually the kind of the inverse of the worship on, right? Kind of the inverse of the worship on x. And then you notice that this under the Frobenius is mapped x1 to the power p, x2 to the power p. But this is again by the definition of RA exactly x, and so Frobenius is surjective.